Hello, everyone. Hey. Thank you all for coming to this talk, and I welcome all of you being at 4 p.m. on a rainy Tuesday. This morning it was raining. I don't know, it was raining now outside. But also thank you for the live streaming audience who are online listening to this talk. I'm Pradeep Nalimelli, just for the introduction's sake. I'm working as a networking and security systems architect in Xilinx data center BU. And I'm experienced in this networking and security domain for a decade and a half. And I'm a big advocate of SmartNICs /DPU/IPUs /DSCs, whatever the names that they are in the market. In today's talk, I'm not going to talk about why SmartNICs. I guess most of you know why SmartNICs. Or if not, if there is anybody who is new to SmartNICs concept, I think by the end of this presentation, you'll get some high-level detail on what SmartNIC is. But today, I'm going to talk about what Xilinx has done to make a SmartNIC in the last 1 year. What are the key values and objectives that we have followed fundamentally as foundation? And then all along the execution of U25N, which is our SmartNIC, which has 2 by 25 gigs on it, we have addressed the needs and challenges of current-day enterprise data centers and Tier 2 cloud service providers. So I'm going to take you through that, and then that will give you a high-level story about what is this U25N and how we successfully could be able to execute it in the last 1 year. I'm going to talk about 5 key values today. In order for a SmartNIC to be a SmartNIC, first of all, it should be a NIC. It should be able to handle traffic at the line rate. It should be able to pull and push the packets into the host, out of the host at line rates. And at the same time, it has to do a lot of stuff like RSS, checksum validation, verification, TSO, LRO, all sorts of stuff. So it has to be a NIC first. So for that reason, Xilinx has used a chip called X2, which we got from SolarFlare. Xilinx has acquired this company a couple of years ago. So we use that ASIC chip, which does all the foundational NIC stuff. It is interfacing to the Gen 3 by 8 towards the x86 side, towards the host side, or any other server. And there's that cute little block, the red block over there, is a Xilinx flagship MPSoC product. It has 4 ARM cores, and it has a reasonably sized enough programmable logic to offload any network solutions, accelerations, offloads. It's a small half-height, half-length. It's passively cooled. Speaking of which, I have one of these cards with me right here. This is a cute little card. It has 2 25 gig ports, PCIe Gen 3 by 16, but we have activated only Gen 3 by 8. It's spec'd at less than 40 watts. It has 2 DDR components on it, 2 gig that talks to the FPGA, and 4 gigs that talks to the ARM processors out there. It has a satellite controller, which will allow the servers to manage in-band and out-of-band. So it has an X2, and the FPGA is sandwiched in between the X2 and the wire side MAC. So the FPGA works as a bump in the wire acceleration right there. Any packet that comes in or goes out has to go through that red block, and where we can offload a lot of stuff. What we have done. First of all, to offload any of the network infrastructure onto it, we need to have some kind of a base platform. The FPGA by itself is a blank if you don't have some kind of an infrastructure that runs and let you run your own offloads. So for that reason, we have come up with something called the shell. We call it inside a shell, but it's a networking base platform. When you buy this card, or when anybody gets this card and plugs in a server, this is what it comes up with. The whole blue block that you see on your right side is the shell. We call it a shell, and which will allow us to load dynamic functionalities on the green block, right? So it will be a basic foundation, a basic NIC by default. Now the shell will allow us to talk to that green block. The shell will allow us to talk to the host towards the X2 and to the Gen 3 by P. And then it also allows us to do some security, logistics. It has a bunch of blocks over there. Each has its own unique functions. You don't have to worry about DMA, MAC side, all the control. Everything is taken care of the shell. Now, when the card is plugged in, you'll get the card enumerated. It will be a NIC card, and it does the FPGA is just doing the pass-through. Now, the shell will allow us to write some offloads. Now, these offloads can be anything. Imagine whatever the problem, the pain points that you're seeing in the enterprise or in your data center, right? It could be a simple crypto. It could be a L2 switching or L3 forwarding. It could be compression. It could be analytics. It could be regex, DPI, whatever. You get a packet. You want to do something out of it, and then send it into the host. Getting packet from the host, you want to do something out of it and send it out. These can be offloads, which can range anywhere. This is the basic architecture that U25N comes up with. Now, what we have done after that? Of course, we have come up with our own turnkey solutions, but then this is customizable. Anybody can write their own code. It could be P4. People who don't know about FPGAs, it's new to them. P4 is generally a high-level language. It contains the semantics for you to look at the packet, take an action out of it. Or it could be FPGA experts can write their own RTL, other stuff. Now, what solutions we have come up with? We have built in 3 to 4 solutions out of the box. I don't want to go into details about architecture. I just have only 20 minutes here. But then today we are coming up with OVS, IPSec, firewall, and QoS. Trust me, most of these blocks, OVS, which does match action engine, IPSec, which does packet parsing and applying crypto, firewall, there are some rules, access control policies. Look at the packet, whether you want to pass the traffic, drop the traffic, or mirror the traffic. All of them has been done on P4. 80% of which is implemented in P4. So FPGA knowledge, I would say, is not really required for you to put an offload right there. And we have the Linux subsystem on the left side, on the right side on the top, on the left side on the top. So we have strong SWAN that we have used for IPSec key negotiation. Initially, 2 parties want to talk. They need to negotiate the keys. The data plane is offloaded to the FPGA. Open vSwitch, which is an open source distributed virtual multi-layer switch. The whole purpose of OVS is to provide a switch-like functionality for hardware virtualized environments, at the same time maintaining the protocols and standards. We have done IPSec. IPSec is IP security. For you, most of you know today, we are all connected to our home offices to the offices using VPNs. What's happening? The packets are all encrypted. Nobody can snoop in and sneak in, right? So the packet is being authenticated and encrypted on the way out. And so on the other side, somebody will authenticate it, make sure it is coming from the right source, and then it will decrypt it and send the plain packet into your LAN. IPSec has been offloaded there. And then firewall, everybody knows firewall is, today it's not, firewall won't sit at the edge. Every server is a firewall by itself. Every server has a distributed firewall. It runs a bunch of VMs, containers, or whatever. Every packet that goes into this compute instances needs to be firewalled. So IT guys have to write some rules whether to accept these packets or not. The firewall can be offloaded right there. We have used NF tables for that. So take the NIC, use the open source OVS or NF tables and strong SWAN, and enable hardware offload on U25N. It will offload. It's not proprietary. It's completely open source. What's next? Now that we have it, what are the advantages of U25N? I would say when you plug in this card, this is a basic NIC. Yes, it can take in packets, consume, and then send it to the host. Now, I would like to do an OVS offload. Now, this NIC becomes a OVS offload SmartNIC. It is doing switching. It can switch the packets from port to VM, VM to VM, port to VM, port to port, all directions. Everything is offloaded right there. The host doesn't have to look into these packets and switch them. The same card, it can take the functionality of OVS and IPSec. when I complement switching with IPSec, now the crypto is as well offloaded. Now packet comes in, it does the switching, it does encapsulation, it does encryption and sends out. On the other side, it switches, decaps, and then decrypts. The third one is firewall, the same card. Now we are leveraging the advantages of an FPGA here. FPGA is good for dynamic configuration, being adaptable, being seamlessly programmable and deployable, right? The same card can take all these personalities. These are the turnkey solutions that Xilinx has been providing, but then you don't have to stick with them. You can write your own code. Take a P4, a high-level language. That P4 can be programmed using our YTestNet stack, and then that will convert that P4 into a bit file that goes and sits in that block right there, and then use it. On top of it, you can use the existing solutions like switching plus your own secret sauce. I mean, switch and do some sort of your secret sauce that is necessary for that's a pain point for your enterprise today, for let's say. It can be anything. As I said, there are a lot of things that can be done using P4, can done in the bump-in-the-wire acceleration method. There is something called SDNet that's available on our website. Today, we are calling it as YTestNet. Anybody who don't know anything about FPGAs don't have to worry about like how do I write an RTL code, right? So take a P4. P4 is like a much simplified version of, I would say, C, much better than that. A 100-line code can be converted into a 1,000-line code in C. A P4 code contains the semantics. It looks at the packet, matches the 5-tuple or 7-tuple, take an action out of it, and then it continues in a loop. It's that simple. So we take the P4 code. You can actually run a behavior model on the left side without even putting on the hardware. On the right side, there's an RTL simulator. Get your logic right. Make sure everything fits in. And then the last process, you can actually fire it. So you'll get a bit file, and that bit file can be put onto U25N. And boom, it takes that offload. There is a demo in our booth where you can actually get more details on how I can take a P4 code and put it on our SmartNICs. And the last key value that I want to talk about is we have the base infrastructure. We have a high-performing NIC, low-latency, high-performing NIC. We have the solutions. We have customized way of writing your own code. Now, what is the performance? What's the saving? How much I can save with this card deployed in the servers? We have done a lot of benchmarking. We have used tools. We have used Ixia, RFC 2542. We have done lots of measurements, latency, frames per second. And we compared with software versus hardware. Having a U25N acting as a basic NIC, let's say if I run OVS in software, meaning the packet has to go all the way into the host and then get switched out or switched into the VM. I don't go beyond 7 to 8 gigs today. If I want to increase this to more, I have to add more and more cores to it. That means you're losing cores in the server. Now, when I offload OVS on the U25N, now this NIC will take the personality of switching. I get 25 gigs. This is measured data, and we have a lot of data to match. We have, in fact, the 10 gigs that I have talked about in the software is it with the biggest packet size of 15, 18. I'm talking about 25 gigs, 64-byte on hardware, small packet performance. Similarly, if I add IPSec on top of it, meaning you have to do crypto. Crypto is CPU-intensive job. Every core has to go and run that algorithm before switching it out. So I would get today on either AMD or Intel process servers. We have done measurements on both of them. I don't go beyond 3 to 4 gigs. Now, when I offload OVS plus IPSec on the SmartNIC, I get 25 gig line rate. We have data on it. I get line rate 256 byte with OVS and IPSec completely offloaded onto U25N. What does it do? It does switching. It does encapsulation and decapsulation. It does AES, GCM, encryption and decryption. Everything onto the FPGA right there in U25N. There is a demo that is running in the booth where we can we have the comparison data between software and hardware. When we enable hardware, there's a simple, the way to run this is like if you, in the strong SWAN, you just have to mention, I want the offload. Then it goes on to U25N. If you don't want, it runs in software. That's how we measured it. The numbers are clearly contrasting. And finally, we use NF tables, which is IP tables kind of a thing. You can put your own policies on your FPGA, and then it will look at the packet and whether it accepts or drops. So in the software, every packet has to go all the way into the kernel. You know kernel is very CPU intensive. There's a lot of context switching happening there. Every packet has to go and hit that NF table, contract, and net filter hooks inside the TCP IP stack. When we offload that onto the software, onto the hardware, the whole tables will be there inside the FPGA. That's how we do accept or drop. So you save 100% of the course. You don't have to deal with the packets. Let's say if all the rules contains dropped. You don't have to see these packets inside the server. You can just drop it right there. You can write your own P4 code and then apply this on U25N today. The whole firewall has been written in P4. OVS is 80% written in P4. OVS plus IPSec is 80% written in P4, except for the IPSec crypto part. We have a lot of data to back it up. The dials are good. The animation is good. But then we have a lot of data as well to show how much difference between software and hardware. And there's latency-wise, we are doing 10x better. Small packet performance is 40x better. We have frames per second. We have cut-through latency. We have throughput measured with RFC 2544 test cases. And then the last thing that I would like to talk about is the power, right? So we are doing a lot of things on FPGA now. What's the power, right? So it's an FPGA plus ASIC sitting in a single card. So we ran 50 gig bidirectional traffic with doing some switching. And both X2 and FPGA are completely occupied with packet processing. We see the performance, the power hitting 34 watts. So the card is spec'd at 40 watts. At highest performance level, the card is doing 34 watts. That way, we are good at power as well. With that, all the 5 key values that we managed to execute over the last year in getting this product out of the board, out of the factory. It's a high-performance, low-latency NIC. It has the base platform technology that we have provided as part of the shipping. The card will be having the shell programmed at the operations, and once you plug it in, you get that. We have the offload turnkey solutions that you can take it from our SDK. If not, you can write your own custom pipeline. It's programmable, accelerated functions. It's deployable, seamless, dynamic, adaptable, whatever FPGA is good at. And it is high performing and saving a lot of TCO for the customers using performance per watt per dollar. Thank you. Any questions?
When you test the traffic test, where did you generate the traffic? Did you generate the traffic from inside of the server and going towards the outside, or did you generate the traffic from outside to towards the inside?
Okay, the question is, when we test it, where did we generate the traffic, whether it is from the server or it's from the outside? So we have done all sorts of testing, right? So we have done VM to VM testing where 2 VMs are running inside the server, and then one VM generates the traffic and the other VM gets it. And we did it bidirectional. That's server generating the traffic. We have tested port to port. We have tested port to VM traffic where there's IX network running RFC 2544 test, and then we generated traffic from outside. We also tested with 2 U25 gig NICs talking to each other, run some VXLAN traffic as well. We also tested interoperability with other NICs as well outside. So one side U25N, the other side could be Intel, Mellanox, or Broadcom NICs.
Do you think this would scale up, this kind of architecture would scale up to like a 50 or 100 gig NIC?
This is 2 by 25 gig card,
okay.
So it could do up to 50 gig.
So if you wanted to go to
Yes, so the whole story is on U25N today, but we have 100 gig NIC called SN1000. It does come up with a similar architecture. So it's right now available, and the only difference between U25N and SN1000 is on U25N we have an X2 sitting and doing the basic Ethernet basic NIC functionalities. On SN1000 we have that NIC implemented in the FPGA, and we call it as a soft NIC. Apart from that, everything else is the same. In fact, SN1000 comes up with more bells and whistles for 100 gigs stuff.
So your P4 programming model is there, you have a fixed pipeline, and sorry to use the word fixed in an FPGA talk, but you said fixed pipeline and then somehow you're mapping the program into it, or is it like a fully mapping into FPGA?
It's fully mapped.
Compiler is really going,
yes,
building the custom tables and
that's right.
Whole thing.
So P4, there is nothing that we have done proprietary for P4, first point. Second point, you take P4 semantics. Typically, P4 has a parsing, deparsing, and a lookup. So you can mention what content in the packets that you want to match, and how do you want to look up. The lookup can be an exact match. It could be a wildcard. It could be longest prefix match. It could be a range. P4 gives you the semantics on how do you want to define it. Based on how you define it, you get the mapping in the FPGA logic has STCAM, TCAM, or BCAM tables. And then you can do routing, you can do forwarding, you can do switching, you can do header manipulations, you could do NCAP, DCAP, all sorts of things. Whatever P4 can do, we could able to transform that logic using that WiTestNet tool into a bit file, into an FPGA logic, that you can test it with the behavior model, RTL simulator, and you can actually use it on the hardware as well. You can expand whatever the space that is available on FPGA, you can use all the space to generate as many tables as you want. The limitation is the space. If you want 2 tables with million entries versus 10 tables with 500K entries, up to you. Any more questions? Please. That's right. So let's say I take the, what is the 80% that I talked about? That's the question. So in the case of IPSec, right? So in that case, it's less P4 and more RTL. So when a packet comes, you need to parse, look at the header and parse the tuples, and then look at the security policy database. If there is an entry in the security policy database saying that, oh, this packet needs to be encrypted, now you go and do encrypt, right? So there are a couple of parsing and lookups existing. We use P4 for that. And then for encryption and decryption, we use the RTL IP. So that's a combination, it's a hybrid. So as the action becomes more and more complex, probably either you have to use P4 plus something else or existing IPs. It could be compression, it could be deep packet inspection, it could be regex. There are some parts which you can write in P4, but some parts may not. In that case, you can use this RTL and HLS stuff. 80%, yes. 80% is 100% P4 component, and 20% is an IP. And Xilinx provide a bunch of libraries for you to. Sorry, I didn't get that question. Right. That's right. The compiler would take care of it. So as an user, you don't have to worry about how it gets translated in the FPGA. For that, we have a huge tool and a huge team, R&D team in Xilinx that will come up with a protocol stack that will compile that P4 or P5 or in future P6 or extensions into a bit file. I think my time is up. Thank you.